Hello. I'm going to go through the bonus project, graphing pressure coefficient by theta for Fluent. So I'm starting in my project 3. I'm just going to use my geometry and mesh from project 3. So I'll go ahead and just drag a new one of the fluid flow. From there, I'll drag geometry to geometry and drag mesh to mesh just to copy it. And then from there, I'll go to setup, open it up, build precision, and start. I'm only going to do the Reynolds number for the 2.6 times 10 to the 5 case just to save time. It's the same for all of them. So now we just wait for this to load. All right, so go to models, go to viscous. For the inviscid one, you just select inviscid, and I just did a velocity of 1 meter per second. But for all the others, I did K epsilon with enhanced wall treatment and then pressure gradient effects. And press OK. And to find the velocity you have to use, I just solved for velocity using the Reynolds number equation and then see viscosity given and the diameter of the sphere or the circle, which for me is just 1 meter, because I just have a 1 meter circle. So once you have that set up, you're going to go to boundary conditions, make sure outlet's pressure outlet, that's fine, symmetry, wall, make sure inlet is velocity inlet. And then for the 2.6 times 10 to the 5 Reynolds number, the velocity you want to use is 3.7979. So once you have that, you just press apply, close, and that's it. Check your reference values. Make sure you compute from the inlet and reference zone surface body. Make sure velocity is what you put, just not. Let me go ahead and check that out. Yep, so that's been saved. Apply. Try it again. There we go. Velocity is what we inputted, still surface body. And then you're going to go to monitors, residuals, 1e to the -6, and just copy that down the board. Press OK. And then go to methods, simple, second order, presto, and then everything else looks fine. Yeah. So I think that's it for setting up Fluent. Let's go ahead and go to initialization and initialize. All right, and then go to calculations. For my project, I did it with 2,000 iterations for each sample, just to save time. I'll just do 500 and calculate. And you just have to wait for it to run. Whenever it wants to run. While it does that, I'm going to get my computer charger. So it's starting now. Tool completion. Now you're going to go back to your workbench, open up results. Go in the post. Wait for all to load up. I don't know why it's taking so long. I guess you can close Fluent. Hopefully it makes it run faster. All right. There you go. So to create the data, we're going to go ahead and right click where expressions is, just hit new, and just call it data expression. Doesn't really matter what you call it. And then you're going to do a cosine in parentheses negative x over the radius of your cylinder or your circle, mine's 1 meter in diameter, so 0.5 meters for me. 0.5. And then to specify the units, so bracket, put the m for meters, close bracket and close parentheses, and then hit apply. And then you're going to go to variables, right click, hit new. This one just say data. And then the expression, you're going to go down and find your data and press apply. And same thing for the pressure coefficient, right click and hit new. Pressure coefficient. For pressure coefficient, it will be pressure and it will italicize parentheses or slash for division and parentheses, and then 0.5 times the density, which is 1.225 for air, times velocity squared, which the velocity we used was 3.7979, and caret squared, close parentheses. And so that's for your pressure coefficient. Go to variables, same thing, CP, find pressure coefficient, and apply. Now you have these two. You're going to go ahead and go highlight wall, highlight symmetry, and then you're going to go ahead and zoom into your cylinder. I don't have a better way of zooming. I'm sure there is though. And you see there's gap. It's not a 2D surface. It's a 3D surface. So you're going to go to location, polyline, and you can do cylinder surface. Then you're going to do method, boundary intersection, and then you're going to do from boundary list wall intersect with symmetry 1. And then you'll see your meshing and everything. And then after that, you just press apply. Once you have that, this is in my way. Then you go ahead and press chart, and it gives you CPV theta. Again, it doesn't really matter what you name it. Data series, you're going to use cylinder surface. X-axis, you're going to use, not that. You're going to use theta, and then y-axis, you'll use CP, and apply. Hopefully it all looks good. Yeah, so it starts at 1, and it has that parabolic shape and trails off. And so then once you get this, you'll go ahead and export your data, name it whatever you want, keep it CSV. You'll open in Excel, or I did it in Google Docs, put it all into one file, and then create the graph for it. And that is pretty much it for this project. You just use this for every Reynolds number, and then for inviscid flow, you just use the inviscid selection where you do K epsilon. And that is it. Thank you.